This stream, we are going to do a review of molarity. We're going to learn about how to calculate molarity for ions after, like in solution, after ionizations. We are going to learn solution stoichiometry, like in general, with precipitation and taking in account the limiting reactants. Okay, first, a review of concentration of solutions. When we do chemical reactions, often take place in aqueous solutions. That's why solutions are so important. So to do stoichiometric calculations, we must know the nature of the reaction. This is the components of the reaction itself. And also very important is to know the amounts of chemicals present in the solution. So that would be, for example, the molarity. The molarity of the solutions. Do we remember how to get the molarity of solutions? Okay, before molarity, do we remember how substances hydrate? How do we dissolve substances in water? If we remember from previous units, substances dissolve in water by a process in which the water molecule, which as we know is polar and it has an oxygen that is partial negative and two hydrogens that are partial positive, this molecule will surround the ions in this way. It will surround the positive ion, the oxygens partial negative will surround the positive ion, and the positive part of water, the hydrogen, will surround the chlorine molecules. So the ions on a grain of salt will separate, and that's why it appears to disappear when we dissolve salt in water. Since ions are so small, we are not going to see them. We're just going to see as if it were pure water. So this is what is happening when we dissolve in water ionic salts. Now, salt is table salt is very easy. We have them in a ratio of 1 to 1, but sometimes the ratio is not 1 to 1. For example, here, cobalt 2 nitrate, when it dissolves in water, it dissolves into the ions cobalt 2 plus and 2 ions of nitrate, because this substrate means that we need 2 ions per every cobalt molecule. So in this case, we are going to have 1 cobalt ion per 2 nitrate ions in the solution. Okay, a review of molarity. Molarity is moles of solute per liters of solution. So just an example of how to calculate molarity. We have 10.5 grams of solid sodium hydroxide in enough water to make 1.5 liter of solution. What is the first step, Steven, to get the molarity of this problem? Exactly, we turn grams into moles, right, using the molar mass, and then we divide by the liters of the solution. So, and that's how we will get molarity. Now, if we are going to get the molarity of ions after ionization, we have to consider the subscripts of cobalt and nitrate or of any ions on the problem. So, for example, if we have 0.5 molarity of cobalt to nitrate, we will have to consider that per every ion of cobalt, we will have 2 of nitrate. So what would be the molarity for each of these ions? Okay, the molarity, okay, no problem. You will know right away. The molarity for these ions, you have to, this 0.5 molarity is of the whole thing, of the whole chunk. But we need to remember that it divides into ions. So we consider the ratio now of 1 to 2. So now what we are going to do is the molarity of cobalt would be identical of the whole thing because it's in a ratio of 1, but the one of nitrate we will have to multiply times 2 because per every cobalt we have 2 of the nitrates. Is it clear? Okay, yes, pretty easy. So now let's go to another example and maybe you can now answer this one. What would be the concentration of each ion now in this solution? A solution of iron 3 perchlorate. Exactly, very good. The answer is 1 mole of iron to 3 molar of perchlorate. Yes, that's how we do the molarity of ions. Okay, now imagine that we have this kind of problem in which they ask us again to the concentration of each ion in solution, and they mix now 2 solids in water. So we have 10 grams of calcium chloride and 20 grams of sodium chloride, and they're diluted in a total volume of 500 milliliters. Okay, notice the ratio here of the calcium to the chlorides. We have 1 calcium per 2 chlorides, right? So the first thing that we're going to do is we're going to change grams to moles, and then the calcium ion moles are going to be the same as we did here, but for chloride, we will have to multiply times 2. And then we're going to do the same with sodium chloride, change grams to moles, and now the ratio is going to be 1 to 1. So let's start working that out. Okay, this is I always organize. It's always a nice idea to organize your problems with given, required, analyze, solve. And then it's easier to read and work back your way to the problems. Okay, so as we mentioned, 10 grams of calcium chloride, we use the molar mass, right? And we have this amount of moles, 0.0901. Now, the same amount will be for calcium, but double of that amount would be for chloride. Now we need to do the same thing for sodium chloride. So now we start with the 20 grams of sodium chloride. Again, molar mass to get to moles. And now, since the ratio is 1 to 1, we will get that amount of ions, 0.342 ions of each for sodium chloride. So we are going to have from calcium chloride, these many amounts of calcium and chlorides, and sodium and chlorides from sodium chloride. Now that we have all the moles, well, we need to add the ones of chloride, since this ion is identical on each, so we add that up. Now, molarity is moles per liter. We already have the moles, and we get the liters from the total solution from our given. So now we're going to do the ratio for every ion from the moles to the amount of solution, and we can get the total molarity of every ion dissolved. Okay, we're going to move on. Okay, so now we're going to start with stoichiometry. The first problem, it says calculate the mass of solid sodium chloride that must be added to 1.5 liters of a 0.1 molar silver nitrate solution to precipitate all the silver ions in the form of silver chloride. So we organize our data with given and required. And remember the stoichiometry Bible from our previous stream? They gave us solution and molarity. So we are here on the green section of this guide. We're going to use this information to change to moles of the given. Then we're going to use the coefficients of the balanced equation to change to moles of B. And then the required was grams. So once we have moles of B, we're going to use the molar mass to change it to grams. Okay, let's start with the problem. So the first thing that we have to do is to do the equation, right? So we have a sodium chloride and silver nitrate. Remember how to do the products? The positive of the first compound will combine with the negative of the second compound. And the positive of the second compound will combine with the negative. So we will, and they already told us that this is the precipitate. It's telling us that the silver ions will precipitate in the form of silver chloride. So this is the solid, and the other one will remain in solution. Okay, what's the first step? What should we do first? Exactly. Very good, Steven. We're going to turn the givens into moles. So we have liters and we have molarity. Remember that molarity is actually moles per liter. So by organizing the data, remember capital M molarity is the same as mole per liter. So if we place it in these units, then we cancel liters and we have moles. The next thing that we're going to do is to compare these moles to the moles of what they're asking for. They're asking for mass of sodium chloride. So now we're going to use the ratios of the balanced equation of sodium chloride to silver nitrate. In this case, we have a 1-to-1 ratio. And what is the last step that we should do if we already have moles of sodium chloride? Exactly. Now we turn it into grams using the molar mass of sodium chloride, and we have our answer. We check the significant figures of the given, 3 and 3. So that's our correct answer, and that's it. Any questions? Excellent. Let's move on. Okay, another problem. In this case, we need to work with the limiting reactant. Remember from before that the limiting reactant is the one that runs out first, and the one which will depend on how much product will be formed. So again, they give us, when aqueous solution of sodium sulfate and lead 2 nitrate are mixed, they're giving us already the precipitate. Lead sulfate precipitates. Calculate the mass of lead 2 sulfate formed, and they're giving us the volumes. 1.25 liters of a 0.5 molarity silver 2 nitrate, and 2 liters of a 0.50 molarity of sodium sulfate are mixed. So now again, we're going to use the green section. They're giving us the green section for the givens. We use that to change to moles. Then with the coefficients, we change to moles of the required. And then again, they're asking us grams. So we're going to use green, yellow, orange. Okay. So let's start. We are going to do both reactants at the same time to figure out which one is the limiting. So we start with the volume. Then we use the molarity to change liters to moles. Now here, we can stop here to decide which one is our limiting. Our reactants are in a ratio of 1-to-1. So if we get these amounts of moles using our given, correct, sodium sulfate is the limiting reactant, correct. So we have two options. We stop here, decide which one is the limiting, and follow through only with the limiting reactant. That's what we're going to do next. We're going to, once that we have this, we're going to move on. We're going to now use the mole ratio of sodium sulfate to the one that they're asking for, that would require 1 mole of lead sulfate. And then we're going to use the molar mass to get to the answer. And checking significant figures, that's our final answer. Any questions? Okay, I am going to show you another method in case that it's not so logical for you to determine the limiting reactant. In this case, it was very logical. Okay, sorry, what did you do after getting the 0.5 moles of sodium nitrate? Okay, so once you decided that this is the limiting, I started again the problem, or you can place the 0.5 moles of sodium nitrate and use these last two ratios that I used here. I just decided to start over from scratch, but you could do the 0.5 times the ratio of 1 to 1 times the ratio of the molar mass, and you will get the same result. I'm just showing the process since the original givens. Okay? Now, sometimes it's not so logical to find the limiting reactant. In case that happens, then you can do both of the reactants and change it all the way to grams, and then choose the smallest amount of product. These are the two possible products. But then you will choose the 152 because it's the least product possible that comes from the limiting reactant. So these are two ways to get to the same result. You use it whatever way you want to, but I find that explaining both ways helps to most of the students. Do we have any questions? Okay. So Stephen, which method would you prefer to use? The one where we find the limiting first? Okay, perfect. Perfect. Okay, let's move on. So another problem. They're asking us to calculate the molarity of each type of ion remaining after solution. I'm sorry, each ion remaining in solution after 20 milliliters of a 6 molar hydrochloric acid is mixed with 50 milliliters of a 2 molar barium hydroxide. And they also added 30 milliliters extra of water. So now they're asking us for molarity, and they're giving us molarity and volume. So now we're going to use molarity and volume, change to moles, and back to molarity for our answer. So green, yellow, green. Okay, let's go back to our problem. And I already placed here the givens, the required, and the equation. When it asks for molarity of each ion, does it mean to find it? Yes, Stephen, the same thing that we did before, but now with our final answer. We'll first have to check how much it reacted, and then they're asking for the ions that are still in solution, the ones in excess. Okay? So let's start here. So this is an acid-base reaction. So it's a neutralization reaction. And in an acid base, if we do the same thing, that the positive of the first compound and combine it with the negative and the other way around, we're going to get as a product water and barium chloride. Okay, so if remember how to get the net ionic equation, Stephen, from the previous streams and previous topics from your classroom? Exactly. You split the aqueous solutions into the ions, correct? And then you cancel the spectator ions. And then you end up with the net ionic equation. So if you do that process, you will end up with this net ionic equation, which is what is actually happening on the reaction above to get to water. Okay, so in this case, it is useful to work with the net ionic equation to find what is really reacting. So let's do that. So we have our initial volume. We are going to multiply. Well, first we're going to change milliliters to liters because molarity is moles per liter. Then we're going to use the molarity. Now we have moles of each. So now we have moles of each of the solutions. Once we have moles, we have to consider again the ratio. So hydrochloric acid is in a 1-to-1 ratio, and barium hydroxide is in a 1-to-2 ratio. So we did as in the beginning, and now we have the molarity of each of the ions in the initial solution. Okay, the next thing that we're going to do is to, with the ions, with the moles of the ions that are in the solution, we're going to think about what is reacting. So the hydrogen and oxygen will react in a ratio of 1-to-1, right? And since we have 0.12 moles of hydrogen to 0.20 moles of hydroxide, we can consider that hydrogen is the limiting reactant. So we can conclude that 0.12 moles of hydrogen will react with 0.12 moles of hydroxide. Questions up to here? Okay. So now we started with 0.20 moles of hydroxide in the original solution minus the 0.12 that actually reacted. We're going to have 0.08 moles of hydroxide in excess. With this information, we can think of what ions were in the solution before the reaction and which ions are in solution after the reaction. Since hydrogen is the limiting, we won't have any hydrogen ions after the reaction. We're going to have the initial 0.12 moles of chloride because this is a spectator ion and it did nothing for the reaction. 0.10 moles of barium, again a spectator ion. And we're going to end with only 0.08 moles of hydroxide in the solution after the reaction. Okay, we already have moles of each ion after the reaction, and they're asking us for molarity. So what would be the next step, the last step? Exactly, we will, well, why 0.5? Steven, what we need to do is divide the moles of each ion into the total liters of solution. So we need to add all the volume involved. If we're going to place everything in the same beaker, the volumes are going to add up. So what we are going to do is we are going to add the volumes, the 20 milliliters of the first solution, the 50 milliliters of the second solution, and the 30 milliliters extra. And we're going to have 100 milliliters of total solution. We turn that into liters, and we have 0.1 liter of solution. Now we're going to divide the moles obtained above by the 0.1. Sorry for this type. I will change it later. So now we divide each moles by the 0.1 liter of solution, and we will get the molarity of each ion on the solution after the reaction occurred. No, what I had extra, what I have, it's just a review of the formula equation, complete ionic and net ionic equation. But we can try another example. I could add another example to the slides later, Steven, like tomorrow. Okay. So what I had planned for the next thing was just a review of how to get the formula equation, complete ionic equation, and net ionic equation. So as you said before, you split the ions that are in the solution, and you keep the ones that are not in solution. So you're not going to split water, right? Because it's a liquid. It's not an ion in solution. So we're going to split the hydrochloric acid into 2 ions of hydrogen and 2 ions of chloride. We're going to split the barium hydroxide in 1 ion of barium per 2 ions of hydroxide. We're going to keep the water as it is, and we're going to split the barium chloride into 1 unit of barium per 2 units of chloride. Okay, these ones are the spectator ions, as we mentioned before, the ones that do not take place on the reaction itself. If we cancel the spectator ions, we're going to be left with the net ionic equation. In this case, since the ratio is 2 to 2 to 2, we can simplify that to ratios of 1. In fact, this net ionic equation will always be the one in any acid-base reaction. Any neutralization reaction in which water is produced will end up having this net ionic equation. And then we can use it for stoichiometry purposes. Was this useful? Okay. Any other question? Yes. Every single, every acid, and when the base has hydroxide, if the acid will always start with a hydrogen, but most of the bases will have the hydroxide ion. In case you have an acid and a base with the hydroxide ion, then yes, this will end up being the net ionic equation for acidic reactions with those conditions. If the base doesn't have a hydroxide, then no, you will have to do it from whatever you have on the reaction. But most of the acid base will have acid and a base with hydroxide. If that is the case, then yes, this will end up being the net ionic equation. So, and that's really simple because you end up with a very easy ionic equation and in which the ratios are 1 to 1. Excellent. Any other question? Would you like me to go to another, again, to review the example of the ions, or to try to type a new problem of the ions? So from my part, that's all. There's my email. Steven, you can email me if you have any other questions. If you have a particular example that you need help, I will add another example tomorrow to the slides. So if you already downloaded, make sure you refresh on the sharing slides. And that's it. Thank you. Thank you for being here. Thank you for your attention. Okay, see you later. Bye-bye.